But let's go ahead and actually get into the meat of today's lecture, which is going to be on more efficient algorithms for inverse reinforcement learning. So this is one of my favorite things I got to work on in my PhD. This was something that Drew, Stephen, and I spent a very long time thinking about. I think it's also a really fun lecture to give in this particular course because on like two separate levels. On the highest level, I think that this is maybe one of the lectures we will see a little bit more about how the design of novel algorithms kind of fits together and how it sort of connects with other things we talked about. In two, I think it'll give you a different perspective on a bunch of different things like hybrid RL and model-based RL we had talked about previously in this course. So hopefully it'll be fun for both of those reasons. So maybe to recap what we were talking about last time, right? We had sort of focused on these three questions. The first thing we were trying to think about is why do we need interaction in imitation learning, right? And at the highest level, this was because if we have these sort of two policies, one that recovers back to the expert support, one that kind of strays off forever, we can't tell the difference between these two policies purely by looking at their, the mistakes they make on expert data. We need to actually try them out, see what happens, and kind of go from there, right? So that is sort of necessary. We need interaction. Then we also talked about how we might need a little bit more, right? Like when we're in this sort of misspecified setting where we can't perfectly imitate what the expert does, we need to be able to tie break between the mistakes that are bad and mistakes that are okay, right? Like we've given these two examples where, you go outside of the support of what the expert does, maybe you do an unnecessary lane change, or maybe you hit another car, right? You won't be able to tell the difference between these two things. And that's where we had sort of introduced a set of reward functions, moments, things like this. So we need some information really about the set of possible reward functions we could be judged under. This is a much weaker requirement than actually knowing the precise reward function we're going to be judged under. And it is often a reasonable thing to ask for it for certain kinds of problems. Then the sort of last thing we talked about is, okay, so we have interaction, we have this set of reward functions, how do we actually put it together in a policy that does well? And we had talked about how we could kind of form this sort of game theoretic objective, right, where basically we say, okay, find me a policy pi such that no matter what reward function I choose in response, even adversarially in this class R, I know that I have some sort of bounded performance difference with respect to the expert. That means so long as the reward function I care about is inside this class, I must also have a bounded performance difference with respect to the expert on that actual reward function we care about. We're going to kind of build on these concepts more today, but any questions about the sort of high-level takeaways from last lecture before we kind of dive in? Cool. So we're going to, yeah, go ahead.
I wanted to ask about the intuition between catastrophic failure and failure in which you can recover from that. In practice, are there settings where it's difficult to tell between the two?
Yeah, that's a good question. So I think it really boils down to what you know about the reward function, right? So if I tell you that this is exactly the reward function, right? This is the thing I'm going to judge you on, then it's very easy to tell whether something's good or bad, whether I can recover from the mistake or not. But if it's a sort of problem where you have an extremely wide set of reward functions, right? Then it's much harder to tell. So think about, for example, having a set of all possible reward functions, right? Then what could happen is, no matter what you do that isn't exactly what the expert was, I can pick some reward function that dings you for doing that, right? And at this point, well, I actually don't know if there's much of a value in doing anything interactive because I tell you as soon as you do anything that wasn't precisely what the expert did, you sort of suffer the maximum penalty. So I would say it really kind of boils down to how much prior knowledge or how much prior information you have about the sort of set of possible reward functions you could care about. So for problems like driving, right, it's actually much easier than you might think to just write down everything you would care about while you're on the road, right? Turns out roads are relatively structured environments. But when you think about things like, I don't know, a robot moving around in the house or something like this, right? Then it's much harder to specify everything you can care about in just an arbitrary person's home. this is why I think a lot of people are in like sort of the robotics community are excited about things like foundation models, because the hope is that somehow by training on the entire internet, you get some sort of like common sense reasoning capabilities that tell you, okay, vaguely speaking, these are the set of things I could care about or most people care about. So I guess what I would say is like, I think yes, it can be a hard problem, but it's a very sort of problem-specific thing, and depending how sort of general or how like widespread the problem is, the specification problem kind of grows with that. Does that make sense? Cool. That was a really good question. Other questions? Cool. So today we're going to try and talk about 3 questions. The first is going to be, what is it that makes inverse reinforcement learning sample inefficient? So we're going to talk about what is it that sort of kind of takes the most compute and the most time in these sort of algorithms. In case anyone is a little bit more like proper than myself, I'm more just sort of interchange between sample efficiency and computational efficiency today, like quite frequently. By sample efficiency here, I mean just the number of steps you have to like, do things out in the simulator or the environment, see what happens. Computational efficiency would technically be the amount of time it takes for me to actually like process those samples and learn the policy and do stuff like this. Mostly speaking, these are kind of interchangeable for tabular problems, so I'm going to kind of ignore that detail for today. And then what we're going to talk about is that really this sort of boils down to the fact that in inverse reinforcement learning, we end up having to repeatedly solve a global exploration, ORL problem, in the sort of inner loop of the algorithm. And this is a very computationally expensive thing to do even once, but I'm telling you, you have to do it at every single step of this algorithm against sort of adversarially chosen reward functions. So it ends up being a thing where you have to spend a kind of crazy amount of compute to actually do this in any sort of effective manner. We're then going to actually talk a little bit more about like, do we actually need to do this and what are sort of a more efficient ways to solve this problem. I'm going to try and give you a concrete example of the first point though before we get into things in too much detail. So let's recap what we were talking about last time about sort of inverse reinforcement learning as game solving, right? So we've written down this game, right, where we say, okay, we want you to pick a policy in your policy class pi, such that even if I adversarially choose a reward function f, I sort of have a bounded performance difference with respect to the expert, right? If I have a, let's say like an exact Nash equilibrium for this solution, for this game, right? I have I actually compute like the equilibrium strategy for this. What does that mean? Like what properties does that let's say that pi star have?
What's pi star?
So let's say pi star is the equilibrium strategy for the policy player.
No regret.
So we can compute that policy via no regret algorithm. But did you mean something else by no regret?
I don't know. Maybe I do.
There. Anyone else? Right. So if we remember right, a Nash equilibrium basically says that if the other player basically gets to choose, in response to what I do, they move second. I basically can't lose too much, right? So for this particular game, right, the sort of, let's say, the expert policy was actually in this policy class big pi, right? Then what we said is, okay, if my adversary, this reward function gets to move second, see the policy I pick, basically try to, pick the worst case reward function response, I basically can't pay too much compared to the expert. So really, my point here is that like the sort of thing I was saying in words about being robust to the worst case reward function is really just sort of inherently a property of a Nash equilibrium in this particular game. Does that make sense? So last time we also talked about these 2 different flavors of inverse reinforcement learning. So we talked about the sort of primal algorithms and these sort of like dual algorithms, right? Where the dual algorithms basically look like doing a best response over policies against no regret against update for the reward functions, versus the primal algorithms look like both players doing these sort of small, steady, stable, no regret steps. And that both of these, if we remember from like Stevens' lectures, are ways we can compute equilibria for two-player zero-sum games. Also, before I get too much into this, who is scribing for today? Cool. Let me know if there are any questions as usual. Okay, so a little bit more precisely, can somebody give me like what the best response over policies was? We talked about this last time. Like if I fix an f and I tell you to give me a best response over pi, what problem am I solving? Exactly, right? Like think about how if I fix an f, the second term goes away. I'm just trying to solve a policy optimization problem. Then that's just reinforcement learning, the thing we've spent, around a third of this class trying to talk about. Okay. Can anyone give me an example of any no regret algorithm? We talked about a bunch of them. Hedge is a good one. Any others? Online gradient descent, good. And we also talk about follow the regularized leader and how all these things are kind of related in some sense, right? So practically speaking, for inverse reinforcement learning, you basically often end up doing something that looks like gradient descent for the no regret step. So we had kind of talked a little bit about this last time, but a sort of core problem I'm going to try and tackle today is the fact that this step right here, that did not come out well, this step right here is really expensive because we need to solve this sort of global exploration problem inherent in reinforcement learning. So we didn't talk too much about exploration in this course, so let me kind of give you a slightly, like sort of the cartoon version of this problem I have in my head at least. So let's say we have the following like tree structured MVP. So basically we're operating in a kind of binary tree, right? So we start at the top and basically we have to make our way to the bottom. And we can think about like the depth of this tree is being something like h. There's 8 steps in this problem, right? So the horizon of the problem, right? And our action space is being left or right at each step. So I guess the first question is, okay, if my tree is of depth h, how many nodes are in the bottom, of the tree?
H.
Yep, to the h, yep. So generally speaking, they're sort of like, there can be an exponential kind of blow up in the state space with the horizon, right? Because as long as you don't have these sort of like two paths sort of like collapse together, right? At every split, at every action I take, things split, right? So we've actually talked about a problem in this class that has this very particular sort of like tree structure dynamics flavor. Anybody remember what that was?
Poker.
Yeah, we were discussing how poker can be broken down into like small node-grid algorithms.
Yes. So poker is a good example. The other example, which is maybe a little bit more in vogue these days, is like language modeling, right? I think about how like if I think of these as a set of like tokens, my like state in like language modeling, right, is just the entire history of tokens appended together, right? So that is a problem where you sort of very clearly have a sort of exponential blow up in the state space with the horizon. So I'm basically, there's no two ways for me to get to the same thing. I'm just appending tokens. I can uniquely decode the entire sequence of actions from the actual state I'm in. So, okay, so for the particular version of this problem I'm going to say that our sort of class of reward functions, our big R here, is just going to be this is going to be just a set of indicators at leaf nodes. So the set of functions look like 1 at one of these leaf nodes and 0 everywhere else. So let's say on the first round I'm trying to solve the IRL game. let's say like F0 or whatever is this. It's like a 1 here and 0 everywhere else. So if I told you that this was the, reward function, can anyone tell me what the optimal policy is here? Yeah, exactly, right? So pi star is going to basically go this way, and then this way, and then this way, right? So pi star is going to look like this. So now you have eyes, right? So you can just look at this thing and say that this is what this is, right? But if you were a computer actually trying to compute the optimal policy here, right? Even if I tell you that the reward is only in the leaf nodes, you still have to check every single leaf node, right? So computationally speaking, the amount of work I have to do per reinforcement learning problem can grow sort of exponentially with the horizon, right? Because I have to check every single leaf node for the actual, this one piece of reward. Does that make sense? Any questions about that? Good. Okay. So let's say we expand, the exponential amount of compute, and we find this one here. Okay, great. We've computed, our let's say our pi 1, right? Cool. Okay. Now we move one step forward. We're going to pick another discriminator, another f, and let's say we pick the following one. We're going to pick something that makes us look really bad, right? The policy look really bad. So maybe what we pick is zeros all the way down, except for a 1 here, right? Now you can imagine, right, that the optimum policy is going to go right at every time step, right? This is what pi star at this round is going to look like. So again, at the next iteration of this procedure, we have to solve another global exploration problem, right? So at every single iteration of this procedure, I'm expending amount of compute that is exponential in my task horizon. And more so, right, if you think about even doing this in sort of an approximate sense, right? The fact that I'm adversarially picking a reward function at every step, right, means I'm going to always pick a reward function for which the policy I just saw wasn't that good. So I'm actually going to have to explore a non-trivial amount to actually compute a policy that does well. So you're going to have these sort of dynamics that are actually not great. The version of this that sort of lives rent-free in my head is that it feels like we're sort of playing a game of sort of adversarial whack-a-mole with like an RL hammer, right? Like I'm basically saying, okay, I'm going to use this extremely computationally expensive procedure to try to whack this mole, and the mole is going to pop up somewhere else immediately. I'm just going to do this over and over and over again, right? So while we talked about why they the properties of solving the inverse reinforcement learning game are very nice, right? Like we avoid compounding errors and things like this. I'm noting the actual process of solving that game seems to be extremely annoying, right? It's solving this whole whack-a-mole problem. Another sort of intuition here that I think is worth thinking about is that in some sense, right, I don't want to make this too formal, but imitation seems like an easier problem, right? Like I've told you what the optimal policy is. I've given you samples from it, right? And reinforcement learning seems like a harder problem, right? Like I actually have to solve this global exploration problem. I just give you the reward function. You have to solve this whole thing, right? And what we've done is we reduced the easier problem of imitation learning to repeatedly solving the harder problem of reinforcement learning, right? As a general principle, like you never want to reduce an easier problem to a harder problem, right? Like, you can always use a bigger hammer to solve the easier problem, but it feels like you're kind of going the wrong way, right? Usually you want to take a harder problem and break it down into easier sub-problems you can actually solve. Also, when I say the word reduction, do people know what that means? Can someone define it for me? I mean it in if you took an algorithms course, I mean it in that sense.
Problem A can be reduced to problem B. If you have a solution for problem B, you can relatively quickly figure out a solution.
Yeah, perfect. Exactly. So it's basically saying that we can, actually, I can't say any better than that. So yeah, I'm just noting here that the sort of reduction we're doing here in kind of traditional inverse reinforcement learning is probably not the one you actually want to do, right? It's very computationally expensive. So, I am going to basically go back to our table here and note that we basically just argue that this class of dual algorithms is going to be inefficient. So now I have a kind of hard question, and I think it's very subtle, but I'll be really impressed if someone can give me the right answer and the right justification for why. So, do primal algorithms have the same problem with exploration? Anybody even have an intuition one way or the other? Yeah?
I mean, I'm just speaking of the derivation, like when we were deriving the online gradient descent algos, we always make the assumption that the response is greedy. So we always have the guarantee that the next step will be better than the step that we've taken before. So it just seems like it's not going to be hurt by exploration as much because we have a very strong assumption.
Yeah. So, for a kind of subtle reason, the answer is yes. So let me try and give you an argument for why. So let's say I have an arbitrary no regret algorithm, right? Just pick whatever one you want, hedge, multiplicative weights, follow the regularized leader, whatever you care about. Can you use a no regret algorithm to compute a best response? And if so, how?
Repeatedly run the no regret algorithm on the current output of the adversary.
Exactly, right? So if I tell you let's say I really constrain the adversary and I just say R just contains the true reward function. So they are always picking the same reward function, right? Then via the no regret property, I have to compete with the optimal policy in hindsight, which for this reward function would actually be the optimal policy, right? So I can just use a no regret algorithm to compute a best response by feeding it the same thing over and over again. And in the limit, it must compute the best response. So this is actually not an issue with the fact that we're doing a dual algorithm here versus a primal algorithm here. Regardless of whichever way you're solving this game, you still, in the worst case, actually do need to solve a global exploration problem. So maybe to just put that in words, primal algorithms also need to explore, as we can force any no regret algorithm to compute pi star by playing the same f over and over again. And I'm just noting here this is also not a property of in particular gradient descent or any particular no regret algorithm. Any no regret algorithm I can use to compute a best response. So these things are, I think that sometimes people think of a best no regret algorithm as asking for a lot more than a best response or something like this. But these things are actually much more related than you might think, right? And then we also talked about how for things that look like follow the regularized leader, right? They almost look like a best response to the history of things you've seen before. But these things are not maybe as computationally different as you might think. Cool. Does that make sense? Any questions about this? And knowing that kind of no matter how we solve this game, you do need to pay in the worst case for exploration. You need to see the entire tree. So let's move on then. So the next thing I'm going to try and give you an argument for is that we don't actually need to be doing best responses in inverse reinforcement learning. All we need to do is consistently compete with the expert. I'm going to give you this argument kind of a more vibey kind of perspective first, and then I'm gonna make it more formal. But like, I think the sort of thing you should have in your head, right, is that like, if at the end of the day, all I care about in imitation learning is performing as well as the expert does, there's no need for me to do this sort of global search over all policies that can be extremely different from what the expert actually was, right? There's no need for the expert to actually be the optimal policy for any of the Fs that are chosen during the inverse reinforcement learning procedure. So let me give you a particular example. Let's say we have the following kind of smaller set of trees. If you guys knew the amount of time I spent like latexing things for like papers, you would think I was insane.
Now you use ChatGPT.
No, I still kind of prefer my artisanal text pickers, you know? Really just does it for me. But, okay, so we're gonna have these two separate discriminators in our class F, right? Or class R, I should say. So this is F1, this is F2, that's the labels inside the things here. And then we can think of the green path here that always goes left as being the expert policy. So given this set of things, right? These set of labels, the optimal policy, pi1, I should say pi1 star here, is going to be the one that actually goes here and kind of keeps kind of self-looping here on the right, right? Same thing for pi2 here, right? Where the optimal policy under F2 is going to go here and just keep kind of self-looping there. So here's a subtle question. Why, when I'm solving an inverse reinforcement learning game, why would the discriminator ever pick something that looks like F1 or F2 versus something that just makes the expert optimal? Like the one that, you know, just goes like this and has all zeros everywhere else.
With the discriminator, you mean basically the adversary, right? That's picking the reward function. And is the question, why wouldn't it not just be zeros everywhere else, because exploration would be as hard as possible, basically?
I guess what I'm asking is, okay, so you could imagine, let's say we say the ground truth R here is just like 0, 0, 1. And it doesn't have this extra plus 1 here.
Yeah.
Why wouldn't I just pick that?
Yeah. I guess it wants to make the difference in J as large as possible.
Exactly, right? Because I'm just trying to remember maximize the relative performance difference between the expert and the last thing I saw, right? That doesn't necessarily mean I have to pick something that makes the expert optimal. I can actually just pick something that doesn't make the expert optimal, so long as it makes the last policy I saw look even worse. So maybe the takeaway though from this though should be that like the actual optimal policy at any round T for the discriminator at that round can be really, really far from the expert policy, right? Because I can just pick, you know, God knows what reward function, and then, you know, the optimal policy can go to somewhere completely different in the state space. And kind of connecting it back to what we were talking about earlier, this means this sort of policy, whether it's pi1 here or pi2 here, can't actually be the policy we want, right? Because we want to actually compete with the expert. We want to behave like the expert does, right? So this policy that goes, you know, to a completely different part of the tree probably isn't the policy we actually want. So the sort of key idea we want to have instead is that rather than at every step trying to compete with pi star of t, we're instead going to try and compete with the expert policy. By compete, I mean basically look at policies that have kind of similar behavior to the expert policy and only look at those policies doing optimization. Because that should be enough, right? If at the end of the day, all I want to do is imitate the expert, I shouldn't need to be looking over the rest of this tree. I shouldn't need to be solving this global exploration problem at every single step. So this is also still going to be pretty vibe space, but let's say we have this right here. So let's say I tell you now that the expert policy for this problem, the expert policy for this problem looks like this. So it goes left at every step, right? Given this information, there's sort of going to be two things you should realize. I'd say the first is that think about how in all the policy optimization problems we talked about before this in the inner loop, I never actually told you what the expert did during those policy optimization problems, right? I just kind of gave you a reinforcement learning problem. I was like, okay, solve it, right? So it kind of seems like we're kind of leaving some information on the table when we kind of ignore completely what the expert did during the policy optimization step, right? The second thing I'll note is that, okay, even though the optimal policy for this particular word function is this one over here, right? It's going to keep going right at every step, right? Given I never want to actually, given I actually want to just compete with the expert, right? I don't actually care that the optimal policy went over this way, right? Like it's just sort of going to a completely out of distribution state from what expert did. So really, I never want to even think about policies that kind of take this right and kind of look at this part of the tree, right? Because it's very different from what the expert did. Similarly, I don't want to ever look at policies that take a right here because those are also going to a completely different part of the state space. Same thing over here as well, right? I basically only want to look at policies that are really looking at states or spend most of their time in states very similar to where the expert was. And this is sort of the intuition you should have in your head of us basically saying, okay, there's sort of this map between global exploration and looking at the full set of policies, right? Like think about all deterministic policies of this problem as being just paths through this tree. All we're trying to say here is we don't want to look at all paths to the tree. We only want to look at paths to the tree that are like pretty similar to what the expert did. So this is the sort of intuition. I'm going to give you formal algorithms in a second, but any questions about the intuition? And is it also clear that like basically by only looking at this part of the tree, I've effectively reduced my search space, right? Because I'm not looking at kind of all leaf nodes, all policies, things like this. Okay, cool. So we're now going to do a little bit of math. I promise it won't be too bad. So I'm going to give you a definition, which is going to be an expert relative oracle, or error for short. It's going to be basically an algorithm that, given a sequence of reward functions, produces a policy in response that satisfies the following condition, right? So let's think about this condition for a second, right? So this condition is saying that, okay, kind of averaged over rounds of this whole process, when I look at the particular adversarially chosen reward function, my performance is not too much worse than whatever the expert's performance was under this particular reward function. Right? Let's say there's a performance bound between what the expert did and what I did. So if at every step I took the kind of the FT I got and I computed the best policy for it, anyone tell me if I'd satisfy this condition? Why or why not? And just for simplicity, assume the expert policy is in your class.
By the way, are you doing cost or reward?
Entirely possible I switched between cost and
I think you're doing reward. Okay, never mind.
Can anyone tell me if I did best responses at every step if I satisfied this definition?
Could you repeat the question once again?
So my question is the following. Let's say we think about even just at a single step, okay? The way I pick pi t is I basically pick the optimal policy under ft. Then do I basically guarantee that I compete with the expert for that round?
Are we assuming you can actually find the optimal policy for FT?
Yes, let's assume you can find the optimal policy, right? But then yeah, right? Because the optimal policy by definition is going to be at least as good as the expert is under this reward function, right? So if at every round I actually did the kind of thing we talked about for the dual algorithms, where I actually compute the best response to this reward function, then I will satisfy this condition, right? Because at every single round, I will say that my policy pi t looks better than the expert under that particular round's reward function. Therefore, summed across or averaged across the round, this will also be true. The kind of key point I'm trying to make here, though, is that we don't actually need to compute a best response to satisfy this condition, right? Like in some sense, if at every round I compute a best response, I do satisfy this condition, it is sufficient, but it is not necessary for me to actually compute a best response at every round. You might not buy this thing just yet. I'll have to actually give you an algorithm that does this, but at least intuitively, you should see that in some sense, I'm going to argue that, bless you, if we can satisfy this condition, I can still solve the overall game. But that I don't need to do best responses to satisfy this weaker condition. All I need to do is, on average, compete with the expert under the reward functions I actually saw. Cool. So this is probably the thing that is a little bit new for this proof. The thing that is a bit older, which you have seen in the past, is just a no-regret algorithm over reward functions. I just wrote it out a bit more explicitly than we did before. So you could think of kind of in the notation Steven was using a while back, that this sort of thing here as basically being the loss function at round t of basically whatever we picked, ft. And you could think of this as being the loss function at round t, evaluated at the best in hindsight reward function, right? So this condition right here, saying that the difference between the sum of our losses and the best option in hindsight goes to 0 in the limit of time, is what the no regret property was, right? And I'll also note that because these loss functions are linear in ft, gradient descent actually fairly rigorously actually is a no regret algorithm here. So you can think of this as just basically being gradient descent. And then maybe one other detail to note here. I have this h over here, right? That's because the scale of the payoffs here is also of order h, right? So we talked about last lecture, any sort of game solving no regret thing, you pay for the scale of the payoff. So I'm just sort of being more explicit about that factor there. So any questions about either the two definitions, or the policy or the reward player? So now let's actually do the proof. One thing you'll notice is that whenever the proof is something I came up with, it ends up being much shorter and much simpler than the rest of the proofs we talk about in this class. So let's go through it in order. So the first thing I'm going to do is say, let's say I use pi bar here to mean the sort of average of the policies I compute over all t rounds of this procedure. So the first thing I'm going to do is sort of expand it out into, rather than having things in terms of pi bar, in terms of the average over iterations of each of the pi sub t's. Can anyone tell me why I can do this?
The definition of your policy basically tends to have probabilities of actions? Or how do you define the policy here?
Oh, you're asking how I define the average?
Yeah, when you take the average, is it
Think of it as I flip a coin, a 10-sided coin, and whichever way it comes up, I play that policy. So it's sort of a uniform mixture over these policies at the start of the episode.
Okay.
Similar to the tower theorem, right? Since J is an expectation over pi, I can use the tower property and get the same result.
Yeah. I would basically say that this is, this is just linearity of expectation, right? Like this distribution right here, right, is just basically like, roughly speaking, like 1 over t sum from little t to big T of pi t. And then I can and remember that j here, right, is just an expectation over whatever the first argument was of the second argument, right? So this is really just the linearity of expectation for me to do this. Let me say that this is just by the linearity of expectation. Next, what I'm going to do is I'm going to upper bound this by taking a max over reward functions in our reward class. So I'm going to say a max over f star in, I should have used just like cal r here, but just the class of reward functions. So can anyone tell me what assumption I'm making when I'm doing this step? Or what needs to be true so that I can bound the performance under R with the max over this class?
The true reward function lies in the class.
Exactly, right? So here I'm sort of assuming like reward realizability, that this function is inside this class. So when I take a max over this class, I upper bound the value I would get under this particular reward function. So this is just assuming reward realizability. Then what I want to do is I'm going to basically recall that the difference between the performance under f star, the best in hindsight, and the actual FTs I chose is just a definition of regret, right? Regret is just a definition between what I did and what I could have done. So this is just sort of like rewriting the definition of regret this way. And then maybe just to complete the proof, let's say we look at this term right here. Can anyone tell me what this term is?
You're about like your policies regret compared to the expert.
Exactly. This is what we said when we talked about these sort of expert relative regret oracles. This is exactly what we said was bounded. The difference between the expert policy and my policy under FT. So this is just that term right there.
Because here, the definition of reg pi is with respect to pi e. There should be pi e somewhere.
Yes, fair enough. I think that, basically we've argued that, things that look like gradient descent can basically actually have conditions such that this will go to 0, right? Over iterations. That's what the no regret property there actually means. What I'm going to now talk about for the rest of the lecture are what are algorithms that basically bound this sort of relative performance with respect to the experts. I'm going to actually prove something slightly stronger, which is that I'm going to talk about bounding it for every t, not on average across t's. But if you bound it at every step, that also means you bound it on average. So, any questions about this proof? Anything that didn't make sense? Really, I'm just plugging in the definitions of what we talked about and assuming we have a word function that's covered in our class. So, okay, so kind of to get to maybe the last question I'm going to try and talk about today is that turns out that if I want to just compete with the expert, all I need to do is do a sort of more local search around where the expert went rather than a global search over the entire state space, right? So think about like that kind of tree I drew, right, where you were only looking at this sort of left part. If I only look at policies that spend their time in that left part, I'm really doing a more sort of like a local search procedure. And local search can't guarantee you compete with the optimal policy pi star. That means you have to search over the entire state space. But the proof I just went through said that I don't actually need to do the thing where I compete with the optimal policy. All I need to compete with is the expert consistently. So essentially the proof I just went through is like saying provably that local search is all you need for inverse RL. So let me give you an example of a particular local search algorithm, and I'll sort of like broaden out this point a bit more. So I'm going to use the term expert competitive RL to mean local search. That's just a little bit more formal way of saying that. Let's talk about PSDP. So Drew talked about this, right? Policy search by dynamic programming. The sort of key idea of PSDP, right, is essentially we reduce the overall exploration problem in policy search by doing resets to states from some good distribution. And in particular, if we want to compete against the expert, a good distribution to reset to is states from the demonstrations. So I'm going to basically walk you through the argument that Drew did just on like a tree structure problem. So let's say that at the second to last time step, I basically get always reset to this state here, right? So I'm at this state here. Let me use a different color actually. I'm at this state here. And what I want to do is pick pi 3, so the policy that acts at this step. So at this step, all I need to do is pick whether I want to go left or right. Right? It's just a single step decision. So which one would I pick, left or right here? Someone say it.
Left.
Left, good, right? So I'm going to pick to go left here. Then sort of like Drew was mentioning, what we're going to do then is lock in this policy. So I'm going to fix this policy. I'm going to back up a time step. Lock this guy in. I'm going to back up a time step. And now I'm going to look at states here, pi 2. I'm going to just try to figure out what do I want to do at this step here, conditioned on the fact that in the future I must go left. So I can either go left here and then go left again, in which case I'll get reward 1. Or I can go right here and then go left again, in which case I'll get reward 0. So again, I'm just going to pick to go left, right? That's going to be left. That will be cleanly. Pi 3 is going to be left, or sorry, pi 2 is going to be left. And then I'm going to basically lock in this policy again. Now I'm going to do it all the way up the tree, right? I'm going to say that, okay, for this sort of top level thing, right? Pi 1, I can either choose to go left and then left again, in which case I'll get reward 1. Or I can choose to go right and then left again, in which case I get reward 0. So what I'm going to do is basically, in total, I'm going to choose to go left here again, right? So think about how in this entire procedure, I only had to explore like states and pick like a single step action, right? I never had to do an exponential search over the entire tree. I just made a sequence of decisions backwards in time. So in total, right, if the depth of my tree is h, I made like h decisions, right, because I learned h policies. And at each of these h steps, right, basically I had to do a rollout from that step and see what happened for each of the a actions. So overall, my interaction complexity is going to be like on the order of h squared. In contrast, remember when you explore the entire tree, you pay exponentially in the horizon. So this gives you basically a reduction in sort of computational kind of complexity from exponential in the task horizon to polynomial in the task horizon. That's sort of the best you can ask for. I'm not gonna go through this more formally, but I'm kind of assuming deterministic dynamics and deterministic policies here. If you don't, you basically end up playing like polynomially in the horizon and let's say logarithmically in the policy class sides. And this is, you can replace with the VC dimension more generally. Question?
So how is this different from just copying the expert?
It's a good question, right? So let's say that here, well, there's a couple different differences, and I think that is the right question to ask, right? Essentially, maybe the meta point I'm going to try and make is that local search is kind of somewhere between global RL and direct behavior cloning. It's kind of in the middle. So one way it's in the middle, right, is for this entire procedure, right, I never looked at the expert actions. I only looked at the expert states. So unlike behavior cloning, A, I don't need access action labels. And B, I could actually, let's say, for example, the expert, I don't know, chose to go this way at this state, right? Like I could still do better than that. So you can compete with policies that look like it. It's not just direct imitation. So I'm just saying try to act optimally at their states, not necessarily choose the same actions they chose. But the sort of point maybe I want to make is that like, well, it's not exactly full RL, right? Because let's say for whatever reason I stuck like a 2 over here, I'm never going to find a policy. So it's kind of in the middle. Does that make sense?
So yeah, so the interpretation is you look at all the states that the expert has been in and try to act optimally in those states.
Right. Conditioned on what you would do in the future. I'm going to give you like a concrete example of like where these are BC and this are different in a bit, but that is a really good question, I think. Definitely a question I had. Any other questions?
How would we do this in an infinite horizon setup?
Yeah, good question. So basically, and I'm going to go through this in a bit, but there's two reasons this is one reason this is an annoying algorithm is I'm learning a sequence of policies, like it's a non-stationary policy. And even if it's not infinite horizon, if my problem is just like 1,000 time steps, right? I have to learn 1,000 separate policies, and that's very annoying. Turns out that it is, roughly speaking, equivalent in theory if I pick a random time step and reset you to it, and you just sort of complete the rest of the episode, rather than doing this whole backwards in time thing. I will state this slightly more formally in a bit. But yeah, that's another really good question. Any other questions? Yeah.
So it seems like we're sort of fixing the prior for the policy learning to be basically the expert and introducing stochasticity in some way by omitting the actions. Like, I'm just wondering, like, from the perspective of the universal solution, good solution for the problem, like if the expert prior is bad and that like in some way bottlenecks you into a search area of the tree, which is basically not good. It's like, are there cases like that where this happens and like
Yeah, right. Like there's no sort of like free lunch here, right? Like either I tell you that, okay, you just want to look at policies in this part of the tree, and I sort of accept that, I'm only going to compete against policies in this part of the tree, right? Or you have to do the whole like global search problem, right? But sort of the thing is, right, is in imitation, we only care about competing with the expert, right? Or competing with policies that look like the expert. Turns out for a really wide set of practical problems, exploration is such a challenge that I would rather have a computationally efficient algorithm that basically looks at policies like the expert rather than actually do this whole kind of like global search over things, right? The same thing is true for like language models, right? The reason we fine tune them is that like technically I could run a policy gradient for an infinite amount of time and I would get a really good language model if my word model was good, but it would just take forever to do this, right? The other thing that is a bit tricky is that you also need to actually say what the reward function is everywhere, right? And for problems like language modeling or imitation, it's often hard to write down what the reward function is. And this means that sometimes even writing down the reward function that's accurate in all the states such that the policy optimization procedure gives you something that's like not crazy, if you could solve it, is also really hard. So for multiple different reasons, like sort of locality is important, both for reducing the amount of exploration, and so that in some sense you don't like exploit the reward function either.
And compared to sort of as the other students had supervised imitation learning, are you arguing that because you learn the intent and not how to reach the intent, you're more robust to new samples? Like basically, why would you advise someone to do this instead of training a diffusion policy or something?
Yeah, I mean, you could train a diffusion policy this way too. But I think maybe the point I'm making here is that like, we will still see, I'll give you like a concrete example of this in like a few slides. I think you guys are asking the right question. So let me think about what I want to cover. So I will. Okay. I think I have time to get to this. So I'm going to give you guys a slightly more formal version of the PSDP proof you did, because I think everyone should see it at least once. And then I will kind of try and get to these questions about why not BC. Does that sound good? Okay. So actually, I can just go through the why not BC thing first, right? There's no reason you can't in general, right? So I think the sort of more subtle question, or a more sort of like precise version of the question like both of you asked is, can this sort of thing just basically give me the same answer as behavior cloning? Can this sort of thing essentially induce compounding errors in a process where I'm trying to avoid compounding errors in the first place? And it turns out in the worst case, the answer is yes. So think about the sort of like cliff problem, right? And once you take A2, you get stuck at the bottom of the cliff, you're kind of screwed. But so you want to try and stay at the top of the cliff for as long as you can, right? So the thing that's kind of tricky, right, is that let's say you have a policy here that makes a mistake, kind of falls off the cliff. But then I basically reset you to a state where you're on the top of the thing, right? You basically aren't able to tell, unless you do rollouts fully under your own policies distribution, that this sort of thing actually is sort of tricky. So maybe let me give you a more concrete example of that. Let's say something like at the first step of this problem, I make an error with probability. Let's say I take this action with probability epsilon h. So like, by which I mean epsilon times h, and then I take this with 1 minus epsilon times h, and then I'm like perfect for the rest of the episode, right? On average over time, bless you, if you average this, right, I'm only making an error with probability epsilon, right? But if I do this sort of epsilon h, right, then I pay a factor of h for the rest of the episode. So overall, I pay epsilon h squared, right? And the thing is basically that it's that nothing in the rest of this sort of procedure, because I'm kind of resetting you to these perfect expert states where you actually haven't fallen off the cliff already, can tell you this, right? Like, in reality, what happens is you fall off the cliff and you just stay there. But because I'm doing this whole backwards in time thing, I always pretend that you actually correctly got the S1 or S2 or whatever, right? So in the worst case, this does cause compounding errors on these sort of like cliff-like irrecoverable problems. But this isn't true for all problems. So let's say we think about this following like very kind of trellis-like problem, right? Let's say the expert takes this sort of like center path here, right? And let's just say that for simplicity, the reward function is anywhere in the top 2 rows is fine. So anywhere here is fine. Now let's say that I've learned the policy that goes straight at every step except for the first one. So at every single step, I kind of go straight, right? Now think about a policy, or trying to pick the action I take here, right? Let's say I don't let you pick going straight here. I only let you pick either going up or going down. Right? If I go up, under my own policies distribution, I'll keep staying in this part here and I'll do well, right? Versus here, if I go down, under my own policies distribution in the future, I'll do quite poorly because I'll stay here, right? But notice that the behavior cloning error of this action versus this action is the same. right? Because BC does not observe the consequences of the future policies you chose. And what matters here is that even though I like made a mistake, that I sort of like didn't do exactly what the expert did, I still like recover in the sense that like it's okay that I'm here. I don't like kind of immediately die and fall off a cliff when I make a single mistake. So my point here is that like the reason something like PSDP will do better than behavior cloning, it actually observes the future kind of consequences of its own policies it shows in the future. And this lets us figure out which mistakes compound and which ones don't. But for you to actually reap these benefits, right, you need to be in this sort of recoverable problem. Or it can't be like you make one mistake and you just fall off a cliff and there's nothing you can do to fix it, right? So I'm not going to do the analysis for this in class because it's fairly complicated, but I linked a paper on the course website where Wen and I did this. It turns out you can basically argue on problems with provisions of recoverability, you can get sort of tighter bounds for these things. But the intuition is this, right? That like on problems like this, I can actually tell that going this way versus going that way was, this was better than that because I know what I'm going to do in the future. This is, I don't for behavior cloning. Does that make sense? Any questions about this? Does that answer both of your questions? Good. I think that's a really good question, by the way. I'm going to note that the other thing that is probably just a useful thing to note in practice is that, you know, if this is sort of like not ideal, the thing that, you know, I and other folks usually do in the experiments for using these sorts of algorithms is you basically mix between the expert state distribution and the ground truth start state distribution. You sort of like kind of mix between doing RL and doing this more local search. So in particular, I think the cleanest way to do this is start off with basically always resetting the states from the expert demonstrations, doing this sort of like very local search. And then over time, anneal towards the actual ground truth start state distribution. So basically then when we're solving the RL problem, you already initialized as a really good policy. So you only have to like perturb it a bit to find the optimal policy versus having to solve the whole exploration problem from scratch. So you can either interpolate or anneal and do things like this to sort of get the best of both worlds, if that makes sense. Okay. So let's see, we have what, 10 minutes? Okay. So I think the PSDP proof is important, but I think that like
We did talk through that.
you guys did talk through it? Okay. So I think
At least I did the pictorial version.
okay, cool. I think then that's fine. Whoever's scribing though, talk to me afterwards, and it would be good to put in the scribe note at least. So let's maybe kind of talk about some of the more kind of practicalities of doing this sort of thing, right? The first practicality is this point about we're loading like H policies, which is kind of a lot to do in practice, right? So kind of like the question somebody was asking, right? We can also do a sort of version of this where we kind of reset to a random time step. So I think the overall picture you should have in your head, right, is that when we're doing kind of traditional inverse reinforcement learning with like an RL inner loop, we're really trying to match like over the whole trajectory at once. Versus when we talked about this thing where we basically do PSDP, what we're really doing is kind of doing this backwards in time, matching over suffixes. We're only trying to match at a single step, conditioned on all the future things I would do after this. Turns out that for most intents and purposes, instead of doing this whole backwards in time careful thing, you can instead basically just reset to a random step in the expert demonstrations and then just try to match over the suffix. And this will sort of give you very similar guarantees. And this allows you to learn like a stationary policy. Because I can just do this at an arbitrary time step. This is another idea thanks to Drew and I guess Stefan called NRPI, or no regret policy iteration. I would say really the sort of practical takeaway from all of this though is that when you're doing something that looks like an inverse RL, in general, it's not a good idea to literally just throw a policy gradient or anything at it. you should basically do something that looks like RL with resets to expert states. And when I say RL here, pick whatever your favorite thing, whether it's PPO, SAC, whatever you want. Usually what you can do, like you guys talked, remember how you like for your course competition stuff, right? You guys had to implement like a gym wrapper. Another really easy gym wrapper to implement is just one where you change the initial state distribution, and you can just do it to be states from the expert demonstrations, and this will speed up a lot of things quite a bit. So that's, I think, one of the ideas to actually get this stuff to work much more efficiently in practice, basically doing a more local search procedure. Maybe the other thing I'd like to note here is that usually when I give this talk, it's usually to people who are like, you know, everyone in the audience is a roboticist, and everyone asks me, how do I actually do resets, right? Like if you were trying to train a humanoid to do a backflip, you can't reset halfway through the backflip, right? You have to learn how to get there in the first place. So hopefully this answer isn't too surprising given what we talked about in this course, but what you can really do, right, is actually just fit a model, and then if you have a model, it's very easy to do resets, right? You just put the initial state into the model and see what future states you get. We had talked a little bit about this idea of kind of hybrid model-based RL, right? In our model-based RL lecture, we fit it both on the expert data and the learner data. Just to sort of maybe reiterate that point, right? Let's say I fit the policy or fit the model just on the expert data, right? What can happen then is, okay, I correctly predict that if you did what the expert did, you will, do well. But I can also be overly optimistic in the sense that I can predict if you do something out of the expert support, things go better for you than they should, right? So think about I don't know, let's say when I take this action, I just say you magically teleport to the goal immediately. This is actually a thing that happens really frequently in practice, right? Because there's nothing basically regularizing you out of distribution to do something reasonable. So you don't want to fit on just the expert data. We had also talked about how let's say the learner goes this way, right? How if we fit on just the learner data, right? Then what could happen is I can be overly pessimistic out of distribution, right? So what I can do is I basically say that, if you did what the expert did, you wouldn't actually do that well, right? So what we actually need is basically to sort of be neither overly pessimistic or optimistic. We want to balance those two things, right? And that's what this sort of hybrid model fitting gives us, right? It tells us that if we do the right thing, we will have a good result. And if we do the wrong thing, we will suffer the consequences. And you need both of these properties simultaneously to basically argue that you have a policy that looks good in the model will do good in the real world. So I'm noticing there's a bit of a nuance here, but so long as you fit the model in the right way, you can basically do resets in the model, and then this actually works fairly well in practice in my experience. In fact, on Tuesday, we'll have a guest lecture from Sanjurban who will be talking about how we've sort of scaled up a bunch of these algorithms to more complicated problems in robotics, and he'll talk a little bit more about that. Please come to that lecture. Then maybe the last thing I'll note is that you can actually use things that don't even have models or resets, and you can also do the same thing. So if you remember the high-Q algorithm that Yuta talked about, right? All of these algorithms, whether they're PSDP, this model-based thing, or the algorithm Yuta is talking about, all of these algorithms are just upper bounding a performance difference, right? So you can use any of them in this overall reduction, right? We talked about how for model-based things, we use the simulation lemma to upper bound performance. We talked about how we use the performance difference lemma to upper bound performance for PSDP or NRPI style things. And if you remember the sort of Bellman error thing Yuta was doing in his lecture, that's just another upper bound on performance. So basically the reason I think this general reduction is really, really cool is that it allows you to basically plug in whatever efficient RL algorithm you have and turn it into an efficient inverse RL algorithm. So it really is sort of a more informed reduction in that sense. So let me quickly step through what high-Q looks like in a slightly more pictorial way than the way you did it. So let's say that I initialize my Q function to be 0 everywhere, and I break ties arbitrarily, right? So then when I roll out my greedy policy pi s, right, it's basically going to pick a random path through the tree, right? Because there's no way to tell what's going on. So you can imagine it basically would go like this, and it would go like this, and it'll go like this. Okay, it gets reward 0, it doesn't update the Q function, right? Then you could say, okay, I'm gonna pick another random path. Maybe it'll go this way, and it'll go this way, and it'll go this way, right? You're gonna just basically explore the whole tree, right? So when you don't use the expert data whatsoever, you end up having to solve this really hard exploration problem. One of the key points of what Yudo was saying was that like we can actually use, he was talking about general offline data, in particular here I'm talking about expert data, to kind of reduce the exploration burden, right? So if I imagine fitting some Q hat both on all of this data and on this expert data, right, things become much easier. Because what I'll see, right, is that I'll say, okay, at this state, I'm gonna call it S2. I know that the optimal, if I acted optimally from this, I get reward 1, right? So like Q star of S2, or let's just say, yeah, Q star of S2 left is going to be equal to 1, right? Now, because I know I can get reward 1 here, I sort of can back it up to the tree, right? So now I know that at the state S1, Q star of S1 left is also going to be 1. And then I can sort of do this all the way up to the tree. So the point here is that like, I basically am using this kind of positive signal I get from the expert data to actually help me do this well. And maybe, I probably should have said this earlier, but just to reiterate, the reason this is actually a good idea, right, is that I'm picking a reward function that makes the expert look good, right? So it's quite likely you'll see positive signal on places the expert actually went to. So practically speaking, what this basically boils down to is basically run some sort of off-policy RL algorithm. So something that looks like Q-learning, if you've heard of things like soft actor critic. Something that looks like that, and you do it with a hybrid replay buffer. So rather than just using samples from your policy, you basically stick all the data from the expert also into your replay buffer. And you basically train on this sort of aggregate data set. If you folks have kept up with some of the work that Sergey's been doing recently, he has an algorithm that does this called RLPD, RL from prior data, and it's literally just this. And a lot of the sort of more recent flashy empirical results from his lab are quite literally doing this.
To just fit back to the lecture itself, like this is for replacing the best response type?
Yes, yes. Yeah, so maybe to kind of put it all together, like Stephen's saying, basically we can replace the best response in our new reduction with this sort of like local search algorithm, right? And pretty much every algorithm we've talked about in this class actually fits the step. So you can do things that look like NRPI, PSDP, HiQ, the algorithm you talked about, and the model-based version of what the sort of agnostic sys-ID that I talked about as well. So I think that maybe in the last minute or two, maybe the last point I want to make is just that I think of like sort of reduction-based algorithm design as something really beautiful and interesting, right? Like most people, when they think about Dagger, right, they just think about the version where you aggregate the data sets over time, right? But if you remember from Drew's lecture and some of the analysis he did, it's really a much more general thing, right? I can run any no-regret algorithm. It doesn't have to be the sort of follow the regularized leader, aggregate the data set things, and I still get strong performance guarantees. The sort of thing we talked about today was a different reduction, this time for inverse reinforcement learning, that gives you computational efficiency without requiring access to a queryable expert, and under some sort of assumptions, also guarantees you avoid compounding errors. And then the kind of cool things about reductions, right, is that they sort of give you like the meta algorithm. They tell you like what the game you're playing is. And then for any particular problem, you think about what is the best sort of like instantiation of that reduction that works like well in practice. So for different problems, you know, if you have access to a good simulator, doing like resets in the simulator to expert demonstrations, like PSDP or NRPI is probably the right answer. Maybe you can learn a really good model, then doing resets inside the model and the sort of like model-based RL things we talked about is the right answer. Maybe you don't have neither of these things, in which case you need to do something that looks more like the algorithm Yuda talked about. Then to prove it works, you need these sort of strong Bellman completeness assumptions and other stuff. But it's really sort of a matter of like, for a particular problem, any of these things that basically look like use the expert data during policy search might help sort of speed up your overall procedure. And I think it's really cool that they all fit in this kind of overall algorithmic template, and you can unify the analysis. Yeah, so that was, I think, why this was one of my favorite things I worked on in my PhD.
So every time you work on a new paper, you said that's your favorite.
Yeah, in like 2 to 3 or like 2 weeks, we'll talk about what my new favorite thing I worked on my PhD is. I feel like that's like the right perspective, right? Like I feel like if you don't think that, it's kind of sad. But yeah, I think that's all I have to say. Thank you all for all the time.